Hello chemistry students. In this video I'm going to go through energy changes in reactions as well as phase changes. Alright, so energy changes accompany chemical reactions, and it is common to observe the temperature of the reaction mixture increasing if energy is released by the reaction, and if energy is absorbed by the reaction, then the reaction mixture is going to cool down, which is kind of weird, but anyways. So if energy is absorbed, the reaction is endothermic, and energy can be written as a reactant, while, by the way, that's the one where it gets cold because energy is being absorbed. And then the exothermic reactions, energy is a product or produced by the reaction, and those are the ones where it gets warm. So for enthalpy changes, the sign is negative for exothermic and positive for endothermic reactions. The negative sign means that the system is releasing energy, and the positive means that it's gaining energy, the system, the chemicals involved in the reaction. Alright, so here's an example. So I've got some sodium hydrogen carbonate, and it's decomposing, and this has a positive enthalpy change. That means that the reaction requires energy to take place, and that means that if you observe this taking place, that it would get cold. Alright, so if we wrote this as part of the chemical reaction, we would show the energy as a reactant on the left side of the arrow. Alright, so here's a reaction pathway diagram that for an exothermic reaction. Notice that we start out with reactants, and then it produces products. And the difference between the energy of the products, or the energy of the reactants, and the peak of the curve is the activation energy. And the difference between the reactant energy and the product energy is the enthalpy change, or the delta H. And see how it goes down, so it's a negative change, which is exothermic. Alright, so for endothermic reactions, the reactants have lower energy than the products do. That means that the activation energy of endothermic reactions is usually pretty large, and frequently endothermic reactions are kind of slow. Alright, the enthalpy change you can see here is a positive value. Alright, so with phase changes, here's an overview of the different phase changes. There's sublimation, where a solid changes directly to gas. You may have observed that happening as ice appears to evaporate in the freezer, and you might think, well, where did it go? Well, it's sublimed. And that has a positive enthalpy change because the solid has to absorb energy to change into a gas. Deposition is the opposite. So that's like where you see the frosty stuff form, freezer burn kind of stuff, where apparently the water vapor, very little bit of it that's hanging out in the freezer, freezes to a solid surface and looks kind of cool and crystally. Alright, so condensation is when a gas changes to a liquid, and that has a negative enthalpy change. And you may have observed that release of heat if you've ever opened the oven or opened a pot of boiling water, and you felt the steam condense on your hand, and it released all that heat, and it felt, it's burning you. So steam is much more dangerous than water, even if they're at the same temperature, like 100 degrees Celsius, for that reason. Alright, so the opposite is evaporation, boiling, vaporization. All of these are the same essential process in terms of energy. So liquid to gas, in order for that to happen, energy has to be absorbed. Alright, freezing or crystallization, so that is the change of liquid to solid. that is a negative change. The liquid has to lose energy in order to become a solid. And then melting is the opposite. Now, if you're trying to keep track of the energy changes, if you move up, the energy change is positive. If you move down, the energy change is negative, or the enthalpy change, I should say. All right, let's take a look at some heating curves. If we're in class, I might do this as a demonstration, or even have you do it. Well, we start out with some ice, just completely solid ice, maybe freeze a temperature into a block of ice, then and then heat it up. You would see the ice gradually increase in temperature, and then while the ice was melting, by the way, it's still all frozen here, while it was melting, you would observe that the temperature would level off at 0 degrees until all of the ice melted, and then the temperature would start going up again and continue going up while you had liquid water until the water started to boil. And then the water would boil, change into steam, and the temperature would stay the same until all of the water boiled off, and then the temperature of the steam would start to rise again. So some takeaways that we can have here is that temperature only changes when there's only one phase present, so solid, liquid, or gas. During the phase changes, the added energy goes into separating the attractions between the particles. So the ice gets, has to be, the structure of that has to be broken down so that the molecules of water can move around each other instead of being locked in a crystalline arrangement. So that's what the energy here is doing. Then the heat of vaporization up here, where the water is changing into steam, that takes a lot more energy, because literally the water molecules, the hydrogen bonds that are holding them together, have to be broken so that the H2O molecules can be separated from one another, and that takes a lot of energy. So that's why this area is longer than this area of the heating curve. All right, so just to summarize that, when you add energy to a pure solid, liquid, or gas, it increases the speed of particles and therefore increases the temperature. Energy added to a mixture of two phases results in a phase change, but no change in temperature. All right, so when we're performing calculations of heat, Q equals mc delta T is used when a solid, liquid, or gas is changing temperatures, like here, here, here. And Q equals mHV is used when you're boiling or condensing, and Q equals mHF is used when you're melting or freezing. Okay, heat of vaporization is the amount of heat energy required to evaporate, boil, or vaporize 1 gram of a liquid substance. HV is the heat of vaporization is also the amount of heat released by the condensation of 1 gram of gas vapor. So it's the same amount of energy. It's positive if it's being absorbed, it's negative if it's being released. Same thing for the heat of fusion. Heat of fusion is talking about the energy required to melt 1 gram, or the amount of energy released by freezing 1 gram of a liquid. From page 1 of your reference table, here are the heat of fusion of water, the heat of vaporization of water, and also the specific heat of water, and notice the different varieties for ice, for steam, and for liquid water. We'll use all of those later. Okay, so if you're doing calculations of heat, we've got Q equals mc delta T, Q equals mHF, and Q equals mHV, just a summary of all the variables and what they mean and what units they're in there. All right, so let's talk through this. If you're heating or cooling a solid, use Q equals mc delta T. If you're melting or freezing something, you use Q equals mHF. If you have a liquid, then you use Q equals mc delta T. And for boiling or condensing or evaporating, Q equals mHV. And then for a gas, Q equals mc delta T. Now, notice that you have different states here. So if we're talking about H2O, water, then we're going to use the specific heat for ice in this calculation, and then the specific heat for water in this calculation, and then the specific heat for water vapor in this calculation. So let's try some problems. Oh, notice that there's not a delta T in these two. Some people will try to put those in there, and I don't know why. Okay, so we're going to calculate the amount of heat needed to melt 23.4 grams of ice at 0 degrees Celsius. Okay, so let's put our chart up here, and let's see, the ice is melting, so there's no temperature change, so this can be solved in one step. So all we're going to have to do here is the MHF, because we have ice, it's at 0 degrees the whole time, and we're just taking it from being ice to being water. So we're moving from here to here, so all we're doing is melting. All right, so only one step there, Q equals MHF, plug in the mass, plug in the joules per gram from the reference table for HF for water, and you should get 7820 joules. Great. Let's do another example problem. So this time we're going to calculate the energy needed to raise the temperature of 15.3 grams of ice at negative 15 degrees Celsius to 5 degrees Celsius. So let's see where we're starting at. We're starting at negative 15. And then we're going to go to 5. So that means we're going to go from all solid, melt it, and then raise the temperature of the liquid some. So that is 3 steps. And recall that we're going to use Q equals MC delta T for the first part of this, Q equals MHF for the melting, freezing part, and then Q equals MC delta T for the liquid part. And we need to use the specific heat for ice here, and the specific heat for liquid water here. Alright, so there's our knowns. We know the ice warms, then it melts, and the liquid warms, so that is 3 steps. And here's our 3 equations. We're going to do that for ice, that for melting, and then that for water, and then add them all up or sum them. Okay, so here's the MC delta T for the ice, here's the MHF for melting, and then the MC delta T for warming. And total, that comes out to be about 5,900, so your answer is 5,900 joules. Alright, so that was great, so let's try a harder one. So this time we're going to calculate the energy released when 23.2 grams of steam at 110 degrees Celsius cools to negative 5 degrees Celsius. Alright, so here's 110, then we're going to cool to negative 5, so we've got to go, we've got to cool down the gas, then we've got to condense it, then we've got to cool down the liquid, then we've got to freeze it, and then we've got to cool down the solid, the ice. So that's 5 steps. So remember, we're going to do Q equals MC delta T there, Q equals MHF there, Q equals MC delta T there, Q equals MHV there, and Q equals MC delta T there, and then add them all up. And recall, make sure you use your specific heat for ice here, and for water there, and for water vapor there. Alright, so 5 steps here. We're going to go through all the things here. Here's all the equations for all of those things, and then we're going to sum them up. So there's the, notice the temperature change is only 10 degrees because we're going from 110 down to 100 as we're cooling the steam. Okay, condense the steam, then the temperature changes 100 as you go from the hottest water can be to the coldest water can be, which is 0. 100 down to 0 is a change of 100. And then we're going to freeze it, so that's the MHF. And then the MC delta T for the ice. We got 5 more degrees to go to get to negative 5. Sum all those up, and then round off to an approximately appropriate number of significant figures. And I reported this as a negative answer, about 70,600 joules. And it's negative because as the water's cooling, it's releasing heat. All right, pressure also affects the phase of substances. And I'll catch that in a second video because I just don't have time in this one. It won't take long though. Thanks for watching.